Hello everyone, welcome to Control Engineering, Mechatronics and Robotics tutorials. In this tutorial series, we explain how to sketch Bode plots of transfer functions by hand. You are currently watching the second tutorial. In this tutorial, we explain how to sketch Bode plot of a transfer function of the first order that has a zero. And in particular, to illustrate the sketching procedure, we will consider this transfer function. The canonical form of this transfer function is given over here. Over here you can see log magnitude subplots that are used to sketch the log magnitude plot of our transfer function, and the final form is given over here. In this tutorial you will learn how to sketch both log magnitude plot that you can see over here and the phase plot that we will explain later on in this video tutorial. But before we start with explanations, it's very important to mention the following. Namely, nowadays we can use MATLAB or Python to generate Bode plots. However, learning how to sketch Bode plots is a fundamental skill that every control as well as robotics engineer need to have. Namely, by learning how to sketch Bode plots by hand, you can obtain a very important intuition about the stability of the system. Then you can even design controllers very quickly. Okay, let's start. Here's our transfer function. The first step is to transform this transfer function in the so-called canonical form. In the canonical form, the transfer function should look like this. It should be equal to some gain k multiplying the ratio of t1 s plus 1 over t2s plus 1. Over here, k, t1, and t2 are constants. The reason for transforming the transfer function into this form will be explained later on. Okay, let's perform the transformation. We have w of s is equal to, from the numerator we can take 0.1 out. And we are left with, what do we have over here? We will have 10s plus 1. Then, in the denominator, we will have, we can take 0.01 out, and we are left with 100s plus 1. Okay, let's further transform this. Over here we have 0.1 over 0.01, and this is actually equal to 10. Then we have over here multiplying 10s plus 1 over 100s plus 1. The next step is to derive the sinusoidal transfer function. The sinusoidal transfer function is obtained from our original transfer function by setting or by substituting s by j omega. Over here, j is the imaginary unit, that is j is equal to square root of minus 1, and omega is the radial frequency, and omega has the unit of radian over second. If you want to know more, omega is equal to 2 pi over t, where t is the period of the input sinusoidal signal to our transfer function. The sinusoidal transfer function has this form. W of j omega is, the gain remains the same, it's equal to 10, and over here we will have, in the numerator we will have 10 omega j plus 1, and in the denominator we will have 100 omega j plus 1. The next step is to transform the sinusoidal transfer function into the polar form. Let's do it. We can do that since this transfer function is a complex number. So gain remains the same, and over here we will have, we need to transform this complex number in the numerator to a polar form. The polar form looks like this. the magnitude or the modulus of the complex number is real part squared, that is 1 squared is equal to 1, plus the imaginary part squared. The imaginary part is 10 omega and we need to square it. And over here we need to multiply by e to the power of j and the angle of our complex number or the argument of our complex number. The argument is computed as inverse tangent function. In mathematics, the inverse tangent function is arc tan. So we will write arc tan, and we will have imaginary part over the real part. That is 10 omega divided by 1. Okay, so this is the polar form of the complex number in the numerator. However, we also need to do the same thing for the denominator. In the denominator, we will have square root of 1 plus. Then we need to square the imaginary part, and that's 100 omega squared. And over here we have everything multiplied by e to the power j and the angle of this complex number. The angle is computed as the inverse tangent function or the arctan of imaginary over real. So we will have arctan and we will have 100 omega divided by 1. And over here I'm going to use parentheses to complete everything. And that's it. This is the polar form of our complex transfer function. From the polar form, we need to extract the magnitude function and the phase function. The magnitude function is usually denoted as m of omega. And we can see that the magnitude function is given over here. That is, it's equal to 10 multiplying square root of 1 plus 10 omega squared over 1 plus 100 omega squared. And this is our magnitude. The phase function looks like this. Usually we denote the phase by phi of omega, and the phase function is, let's see, these two terms can be written as a single e term, where we're going to have, let's write it down over here, we will have j, then multiplying arctan of 10 omega minus arctan of 100 omega. And that's it. That's our term. Consequently, the phase is this term over here. The phase is arctan 10 omega minus arctan of 100 omega. And that's it. This is the phase function. Actually, this is the phase function and this is the magnitude function. To summarize, here is our magnitude function and here's our phase function. The Bode plot consists actually of two graphs. The first graph is the log magnitude function. The log magnitude function is defined like this. It's denoted by capital L and it's equal to 20 multiplying a logarithm with the base of 10 of our magnitude function m of omega. Then the second graph in the Bode plot is the graph of the phase function phi of omega. Consequently, when someone asks you to plot or generate a Bode plot of a transfer function, you first of all need to generate the log magnitude function graph, which is defined like this, and you need to graph or generate the graph of phase function phi of omega. In the sequel, we will generate the graph of the log magnitude function. The log magnitude function is defined as 20 logarithm with the base of 10 of m of omega. And let's substitute m of omega into this expression, so we will obtain 20 log with the base of 10 and over here we will substitute 10 multiplying. In the numerator we will have square root of 1 plus 10 omega squared, and in the denominator we will have the square root of 1 plus 100 omega squared. Next, by using the basic rules of logarithms, we will decompose this function like this. L becomes 20 log with the base of 10 of 10. Then we will have minus 20 log with the base of 10 of this expression in the denominator, that is the square root of 1 plus 100 omega squared, and then we will have plus 20 log with the base of 10, the expression in the numerator, and here it is 1 plus 10 omega squared, and that's it. Now I'm going to call this function as L1. This function with the minus sign will be L2, and this function will be L3. Here's the summary of what we achieved so far. We represented our log magnitude function as the sum of three basic functions, L1, L2, and L3, where L1 is 20 log with the base of 10 of 10, and that's 20. L2 expression is given over here, and L3 expression is given over here. We will approximate our Bode plot by using asymptotes, and to properly define the asymptotes, we need to define the concept of the break frequency, which is also called the corner frequency. Notice what we did from the beginning. We expressed our transfer function in the canonical form that looked like this. W of s was a constant k multiplying over here t1 multiplying s plus 1, then t2 multiplying s plus 1. What's the reason for doing this? Well, the reason for doing this is to obtain this term over here as well as this term. You can see that these terms are very similar. They are 1 plus something squared that depends on omega. And we did this for a particular reason, namely, the canonical term, that is any of these terms, will look like this. I will call them L, for example, I, is actually equal to 20 log with the base of 10, and here we can put plus minus sign, of what? Of, if this term over here was ti or any other number, over here you will have 1 plus ti omega squared. In this case, the term will be 20 log square root of 1 plus t1 omega squared, and the corresponding term in the denominator will be minus 20 log square root of 1 plus t2 omega squared. And that's precisely this. The break frequency or the corner frequency is the frequency for which this term is equal to square root of 2. That is, square root of 2 is equal to square root of 1 plus ti multiplying omega b, where omega b is our break frequency. That is, the break frequency is denoted by omega b, and keep this in mind. So by solving this equation, we will obtain 2 is equal to 1 plus ti omega b squared, or from this equation we have that ti omega b squared is equal to 1. From here, since omega b as well as ti are positive, we will obtain this ti omega b is equal to 1, and our break frequency is actually 1 over Ti. And this is very important conclusion. That's the main reason why we express the terms like this. Namely, by expressing the terms like this, we can immediately read the break frequency. For example, for this term, the break frequency is 1 over 100, and from this term, the break frequency is 1 over 10. Now we are ready to sketch the log magnitude plot of our Bode plot. For that purpose, I prepared this graph template. And let's explain it over here. On the horizontal axis over here, we will enter the values of omega, that is the values of the radial frequency, and notice over here that the horizontal axis is in the logarithmic scale, that is we have 10 to the power 0, 10 to the power 1, 10 to the power 2, etc. On the other hand, over here we will plot the value of magnitude, that is we will plot the value of any of these functions, and the magnitude is measured in decibels. This is very important. Over here I have 4 graphs. First one, second one, third one, and fourth one. I created 4 graphs since on this graph I will sketch L1, on this graph I will sketch L2, on this graph I will sketch L3, and on this graph over here I will sketch L, that's sum of L1, L2, L3, and that's it. Ideally, this graph, and this graph should be below each other. However, I cannot do it on this computer screen. On the other hand, if you're using pen and paper, you could nicely draw first the graph of L1, then below the graph of L2, and then below the graph L3, and then you will sum up everything, and below you will enter the graph of L. Okay, so let's start with L1. L1 is actually a constant, and it's equal to 20, and it doesn't depend on the frequency. Consequently, over here we will have a completely straight line, and this is our L1. Over here I will write L1 is equal to 20 dB. Next, I need to sketch the graph of L2. For that purpose, I will be using asymptotes. To find the break point of my asymptotes, I need to use the break frequency. Over here, the break frequency is obviously at omega is equal to 1 over 100, and that's the point over here. Now, here's my break frequency on this graph over here. For omega values below break frequency, that is for omegas much smaller than this break frequency over here, I can approximate this function as a straight line. Why is that? Well, this term can be approximated by 0 for omega much smaller than the break frequency, and then I will have 20 log 10 of 1, and that's 0. And consequently, over here, I will have a straight line until this break frequency. Then, after this break frequency, my function L2 can be approximated as minus 20 logarithm with a base of 10. This term over here is much more dominant than 1, so 1 can drop out, and we will have over here square root of 100 omega squared, and this is simply 100 omega. It can be shown that the function minus 20 log with the base of 10 of 100 omega is a function that has a slope of minus 20 dB per decade. A slope of 20 dB per decade means that if I increase or decrease my frequency for 10, the function will go up or go down for 20 dB. Consequently, this is minus 20 dB slope. And consequently, I need to draw a parallel line starting from this point over here, and the line should be parallel to this minus 20 dB slope. And here it is. This is the asymptotic approximation of L2. Let's denote the break frequency over here. And this break frequency is given over here. Let's denote it as 10 to the minus 2. Now, and over here I will type the analytical form of L2. L2 is minus 20 log with the base of 10 square root of 1 plus 100 omega squared. And that's it. Now, this is the asymptotic approximation of L2. In reality, L2 does not exactly look like this. It will look like more like this. Over here, we will have a point of minus 3.01 dB, and you can obtain this point by simply substituting the break frequency here, and you will obtain square root of 2, and if you take 20 log with a base of 10 of a square root of 2 with the minus sign, you will obtain minus 3.1. And this is the maximum error that our asymptotic approximation is creating. And consequently, the real function will look somehow like this. It's going to approximate, or better to say converge to these two asymptotes in infinity. However, to make this graph less confusing, I'm not going to sketch the real function, I will just keep the asymptote. And this is the standard practice when plotting Bode plots, that is, always plot the asymptotes since they are very easy to be seen and they don't make the graph to be messy. We repeat the same procedure for L3. The first step is to identify the break frequency. Over here, the break frequency is at 10 to the minus 2. Consequently, the break frequency will be here. Okay, now, for omega values much smaller than the break frequency, we can actually approximate this function by its asymptote, and here it is. Let me nicely write it. Here is the asymptote. Again, when omega is much smaller than 10 to the minus 1, this whole term can be neglected, that is, it becomes 0, and over here we'll have square root of 1, and 20 logarithm of square root of 1 is simply 0. Now, for omega much higher than the break frequency, that is, than this frequency over here, we have the approximation of the function that looks like 20 log with the base of 10 square root, and then this one can be neglected since this term is more dominant for higher frequency, and we will have 20 log with the base of 10 of square root of 10 omega squared, and that's simply 20 log with the base of 10 of 10 omega. The slope of this function is again 20 dB per decade, and again we will have here 20 dB per decade, which again is the slope given over here, and we will simply draw this line. Here it is. This line should be parallel to this line, and this is the asymptotic approximation of our L3. Over here is our break frequency. Let's denote it. Let me turn off this type of typing, and the break frequency, let's call it W3, is 10 to the minus 1, and our function L3 has this form. It is 20 log with the base of 10 square root of 1 plus 10 omega squared. Now we are ready to plot the final graph L. That is, we need to sum the function in this graph, the function in this graph, and the function in this graph. We do it like this. First of all, over here, we need to denote the break frequency. So here they are. The first one is at 10 minus 2. The second one is at 10 to the power minus 1. That is over here. And let's see. Before this break frequency, we can see that our L can be approximated by L1, and that's 20 dB. So let's change the color to match this exact approximation. I need this pink color. That is over here. Our Bode plot or log magnitude plot will look like this. Then what happens over here? Over here at this break frequency, that is over here, our function L2 kicks in and becomes more dominant. And it will decrease this constant with minus 20 dB per decade. And we will have over here a constant slope starting from here until here, until the second break frequency. The second break frequency is at 10 to the minus 1, and at here, this slope, or actually at this point over here, the function L3 will kick in and it will go up with the slope of 20 dB per decade. Since I over here have 20, let me now change this. Over here I have plus 20 dB per decade, and over here I have minus 20 dB per decade. After this point, this minus 20 dB per decade will be cancelled by this plus 20 dB per decade, and what will happen over here? I will have a simple straight line, and let's use this color to denote a simple straight line starting from here, and that's it. And this is our functional approximation of our L, or the asymptotic approximation, better to say, of our L. To summarize, what's happening? Until the first, or better to say, this break frequency, that is WB3, we are approximating everything by a straight line, straight horizontal line. Then at this point over here, the function L2 kicks in with a slope of minus 20 dB per decade. That is, it kicks in here. It decreases the function L with a slope of minus 20 dB per decade until our third break frequency, or the break point over here, where this plus 20 dB per decade of this function cancels this minus 20 dB per decade and makes the graph to be again horizontal, and that's it. This is the asymptotic approximation of L. Next, we generate the graph of the phase function. Here is the original phase function, and let's introduce phi2 to be equal to minus arctan 100 omega and phi3 to be equal to arctan 10 omega, and consequently phi can be represented as phi2 plus phi3. Over here we introduce the notation that's consistent with the notation for log magnitude functions. Namely, the corresponding log magnitude function of phi2 is L2, and the corresponding log magnitude function of phi3 is L3. Over here, we will sketch the graph of phi2. Similarly to the previous graphs, on the horizontal axis we have omega, and on the vertical axis we will have phase expressed in degrees. So let's start with phi2. When omega is 0, phi2 is 0. And this point is somewhere all the left over here. That is, it's outside of the scope of my screen. However, I will denote this point just symbolically over here. The graph should start or enter somewhere here to our graph. Okay, let's see what happens at infinity. At infinity, that is when omega is equal to infinity, we will have minus arctan of infinity, and that's minus pi over 2, that is minus 90 degrees. That is, somewhere in infinity, the function will go to minus 90 degrees. From here we conclude that the asymptotes are 0 and minus 90 degrees. Next, let's see what happens at the break frequency. When the break frequency occurs, that is when omega is 1 over 100, we will have minus arctan of 1, and that's minus 45 degrees. And consequently over here at the break frequency we will have minus 45 degrees, and that's it. These are the 3 points that enable us to sketch this function. And over here, since I don't have any other means, I will try to sketch the function by using my hand. So somehow the function should look like this. It is a continuously decreasing function of omega, and somehow it should look like this. Over here it should pass through this point, and then slowly it should decrease, and then over here it's going to decrease, and it's keep on decreasing until it reaches minus 90 degrees at infinity. Next, let's sketch phi 3. Over here, when omega is 0, we have that phi 3 is 0. That is, at omega 0, we will have 0, and the graph will enter somewhere here. Now, phi 3 is an increasing function of omega, and consequently, we will have at omega is equal to infinity, we will have phi 3 is arctan of infinity, and that's plus 90 degrees. Consequently, the asymptotes are 90 degrees and 0. Let's see what happens at the break frequency. When omega is 1 over 10, we will have arctan of 1, and that's exactly 45 degrees. That is, at this point over here, we will have 45 degrees. And let's change the color such that we can sketch this function. So the function should somehow look like this. Again, I don't have any other means to sketch this function except using hand drawing, so it somehow should go like this, pass through the breakpoint, that is through 45 degrees, and then it will continue like this. And that's it. Let's denote the corresponding breakpoints. This is the WB3, and this other breakpoint is WB2. Okay, now we are ready to sketch the final graph of our phi. We just need to superimpose these two functions, and let's do that. Let's see what happens over here. First of all, we can see that the function phi 2 is dominant over here, and it's dominant until approximately its breakpoint over here. Then we will have another breakpoint, that is the breakpoint of our other function, and let's sketch everything. This function phi 2, let me just type phi 3 actually, will lift phi 2 for a certain value, and we will have some graph that looks like this. To superimpose these two functions, first we need to denote the breakpoints over here on the joint graph. Here is the breakpoint WB2, and here is the breakpoint WB3. Okay, now let's analyze these two functions. Phi 2 function is always negative for the positive values of omega. On the other hand, function phi 3 is positive for the positive values of omega. However, for the same value of omega in this small range, the absolute value of phi 2 will be larger than the absolute value of phi 3. Consequently, our graph will start from 0, and then it will go in the negative direction. That is, it will go down. And over here, we can see that in the negative range, that is, in the range of small values of omega, the decrease of function f2 is larger than the increase of function f3, and consequently we are going to go down like this, down, 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 down. And let's see what happens here at the break frequency. At the break frequency WB2, phi 2 is minus 45 degrees, however phi 3 is positive, and consequently we are not going to hit the break frequency minus 45. And then we will keep on going down, we will keep on going down. Now over here, we don't know exactly the values that our function will take. We are just assuming the values, and we are just sketching the graph. We are going down, and somewhere over here, we can see that function phi 3 and its slope will start to increase. However, the slope of phi 2 will slowly start to wane. That is, it will slowly start to decrease. So we will have something like this, and then the function phi 3 will kick in, and its slope will become higher than the slope of phi 2, and we will have this type of behavior. Where this minimum peak happens, we don't know. We can analytically calculate it. However, from this graph and this way of sketching, we don't know it. And then let's keep on going, keep on going, keep on going, keep on going. And where this graph will end, let's see. The asymptote of phi 2 is minus 90, and the asymptote of phi 3 is plus 90. Consequently, our graph will end here. However, will it pass into the positive region? Well, this is a good question. Let's answer it. We can see that phi 2 in the absolute value is always larger than phi 3. And since phi 2 is negative, we can see that our phase will always stay negative, and it's going to asymptotically reach 0. That is, it will start from 0, it will go negatively, go down, reach the minimum. We don't know exactly where is the minimum. Then it will start going up, going up, and it will asymptotically reach 0 again. And that's all for today. Thanks for watching.